So we're now into the third unit of the grade 11 university preparation physics course, and this is about energy. Before we get into energy, we have to talk about a topic known as work. So you probably are familiar with the word work, but you may not be as aware of the physics definition of that word, so we're going to get into that. So the term work has a very specific meaning in physics. Mechanical work, it's given the symbol of a capital W, is done on an object when a force displaces the object in the direction of the force, or a component of the force. So for example, mechanical work is done when a crane lifts a steel beam for a new building. However, if you are holding a heavy box, you may feel pain and even break a sweat, but you're not doing any work on the box because you're not moving it. So just holding something, even though you're exerting a force to hold that in place, work is not being done. Even though you're exerting energy, you're not doing work. But if you actually move something with a force, then work is done. So mechanical work, the definition of it is work that occurs when a force displaces an object in the direction of the force, or a component of the force. So, what are the factors that determine how much work is done? Well, here we have an image with the person pulling some grocery carts, and if they apply a greater force, then the grocery carts will move a greater distance. So work is proportional to the amount of force that is applied. Another way to look at it, if some objects, in this case the grocery carts, are moved a greater distance, more work is done. So work is also proportional to the amount of distance that an object is moved. So putting those two together, we can come up with an equation for work. Work is equal to force times distance. And that is because work is both proportional to the force applied and it's proportional to the distance the object is moved. So while force and distance are vector quantities, it's important to note that work is a scalar quantity. So work is measured in Newton meters or joules, and it is a directionless quantity. So that is something else to consider with work. So the equation, work equals force times distance, has some limitations though. One of them is that it only applies when the force and the displacement are in the same direction. So let's look at a situation like this. Somebody's carrying a luggage at an angle, so they're pulling on the luggage at an angle. The force they're applying to the luggage is at an angle, but the luggage itself is not going to be moving up at all. It's just going to be moving in the horizontal direction. So in this case, the only portion of the force that's doing work is the horizontal portion of that force. So you'd have to break the force into its horizontal component to determine the work that's done. So it's just that horizontal component of the force multiplied up by the displacement, that is the work. And this slide further explains that. So we could adjust the equation in situations like this, where we say work equals force times distance times cosine of theta, where theta is the angle between the applied force and the displacement. Another way to think of it is you could just always write it as work equals force times distance, and just be aware that your force has to be in the same direction or in the same dimension as the distance that the object has moved, or the displacement of the object. Here's some points to copy down. Work is a scalar quantity. It's equal to force times distance. W is the symbol for work, and it's measured in joules. F is the force. Delta D is the displacement. One thing to note is that a joule is equal to a Newton meter. which is equal to a kilogram meter times meters per second squared. So that's how you can break up the joule into other SI units. And another thing to note is that work equals force times distance only applies when the applied force and the displacement are in the same dimension. Here's a quick question. It says an airport terminal employee is pushing a line of carts at a constant velocity with a horizontal force of magnitude 95 newtons. How much mechanical work is done in pushing the carts 16 meters in the direction of the applied force? And they want us to express this in two ways, one using joules and one using kilojoules. And you will find sometimes with work we will have to express things in larger, or the work done will be large enough to so that expressing it in kilojoules is important, and you might be asked to do that. So here it's simply 95 times 16, and that gives us 1,520. But note that we are given two significant digits for the force and two significant digits for the direction. So our solution has to have two significant digits. So we don't write 1,520, we write down 1,500. And that's what it is in joules. To convert that to kilojoules, we just divide by 1,000, and we're simply left with 1.5 kilojoules. Here's another problem. It says here we have a curler who's applying a force of 15 newtons on a curling stone, and they accelerate the stone from rest to a speed of 8 meters per second in 3.5 seconds. So assuming that the ice surface is level and frictionless, how much mechanical work does the curler do on the stone? Well, here it would be force times distance, but we don't directly have a distance. Okay, so we know in this case work equals force times displacement, of course, but we don't know the displacement directly, although we have a VF, we have a T, and it says it accelerates from rest, so we know our VI is 0. So our displacement can be found using the equation VI over VF divided by 2 times T. And to do that, we know our VI is already 0, so we can simplify this to VF times T over 2, or 0.5 VF times T. But what we can do next is take this and substitute into this equation, so we have only one calculation to do. So F is replaced with 0.5 VFT. Sorry, I should say D is replaced with that. So our calculation becomes 0.5 times F times VF times T. And substituting in, we know that our force is 15.0, so we have 3 significant digits. Our VF is 8.00, which is 3 significant digits, and our T is 3.50, so another 3 significant digits. So our solution should have 3 significant digits, and when we calculate that, 0.5 times 15 times 8 times 3.5, we have 210, and that's in joules. So that's our solution, 3 significant digits in this case. So we talked about work being a scalar quantity, although it could still have a positive or a negative value, and this is because the direction of the displacement could actually be negative. Even though force is being applied, an object still might move against that force. And we'll get into that concept of negative work soon. But first, let's talk about positive work. So positive work happens when we apply a force and the displacement occurs in the same direction as the force. In a situation with positive work, we tend to have an object increasing in speed. So positive work is not as difficult to understand. It's the more common type of work you'd come across. So what then is negative work? Well, first let's define it. Negative work is when the force and displacement are in opposite directions, and the speed of an object tends to decrease. So what's a situation where we have a force applied and an object slows down? Well, a common one is friction. Let's say we have an object moving at a constant velocity, and then it starts to experience a friction force. Well, that friction force, it's applied against the direction of motion, and the object might slow to a stop. So that distance it travels as it slows to a stop would essentially be, you can consider it as a negative displacement and the force being positive, so we would have negative work. Or you can consider it as being a positive displacement and the force being negative because the force opposes the motion. So that's a situation where we have negative work. It happens whenever we have a force trying to slow down an object. Here's a question. We have a toboggan carrying several children. Total mass is 100 kilograms. It reaches its maximum speed at the bottom of a hill, and then it glides 20 meters along a horizontal surface before coming to a stop. And the coefficient of kinetic friction between the toboggan and the snowy surface is 0.10. So we're asked to do a number of things here. We first have to draw a free body diagram, and we have our Fg is opposed by the Fn, but there is no force applied in this case. There's no force moving us forward. We only have the force of friction attempting to slow us down. So there's only an Fk. And then it says to determine the kinetic friction acting on the toboggan. Well, the kinetic friction is the Fn times the coefficient of friction. That is equal to the Fg in this case. So it's mu times m times g. And it's 100 times 9.8 times 0.10. It works out to 98 newtons. So that's our frictional force. So we have a 98 Newton force opposing motion, and we're asked to find what is the mechanical work done by the friction. Well, work equals force times distance. So we have the force of 98. The distance that it travels, let's go back and see in the question, it says 20 meters. So if we want to find out what work is done, it would be, and I'll turn the calculator on for this, let's say we have a negative 98 force because it's opposing the motion, and we've moved 20 meters, so we have negative 1,960. Now I believe in terms of significant digits, we'll have to go back and check, because 20 meters and 100 kilograms, those would be, those are not three significant digits, so even the 0.10. So really our answer should be negative 2,000 for 3C. Why would the work be negative? Well, displacement and force are in opposite directions. And notice that you have to be consistent. So if you're saying that the force is negative because the displacement is positive, you can't also say that the displacement should be negative because it's going opposite the direction of the force. So they either match in terms of their direction or they don't match, and we have a negative. Here we have work done against gravity. So in order to lift an object to a higher position, a force must be applied upward against the downward force of gravity. So if the force applied and the displacement are both vertically upward and no acceleration occurs, the mechanical work done by the force against gravity is positive. So here the applied force is equal in magnitude to the weight of the object. So when you have our applied force, the work that is being done is going to be equal to the force of gravity. So you could also find this out by just finding out what the force of gravity is to lift an object to a certain position. So here's a question. It says a bag of groceries with 8.1 kilograms is raised vertically upward without acceleration, a distance of 92 centimeters. So here it says to determine the force needed to raise the bag without acceleration. So that would be the mass times the gravitational field strength in newtons per kilogram, and that gets us to 79 newtons, because we're just looking at the force of gravity. If we can apply that force of gravity to this object, then we'll be raising it without acceleration. The next part of this question says, what's the mechanical work done? I'll turn the calculator off for a quick second so you can read it fully. What is the mechanical work done on the bag of groceries against the force of gravity? Well, here, if we're raising it without acceleration, right? So we have, we'll come up with that calculation again. The 8.1 times the 9.8 is our force, and we're raising it 0.92 meters. So we have 73 joules of work done. A forklift does 4.0 times 10 to the power of 5 joules of mechanical work on a 4.5 times 10 to the power of 3 kilogram load. To what height does the truck lift the load? So we'll do this one on paper because it's going to involve rearranging an equation. So here we have our forklift truck. So we know that work equals force times the displacement, and we have our work applied. We need to find our mass. We need to find our distance. So the F here can be replaced with an FG, which is equal to an mg. And we need to find the displacement, so we would put D equals W over mg. And displacement equals, when we replace, 4.0 times 10 to the power of 5 over our m, which is 4.5 times 10 to the power of 3, and 9.8. So let's work this out. Okay, so we have 4 times 10 to the power of 5 divided by 4.5 divided by 10 to the power of 3 divided by 9.8. So we end up with 9.07, and we have two significant digits, so we have to round that to 9.1 meters. 9.1 meters of work is done in that case. So let's look at situations where zero work is done. So these are situations where where a force is applied, but no displacement occurs, or I guess the other situation could be when a displacement occurs and no force is applied, or it could be a situation where a force is applied, but displacement doesn't occur in displacement might occur, but not in the direction of the force. So let's look at the first situation I mentioned. If you're holding a toolbox on your shoulder, you'll be exerting an upward force on the toolbox, but since the toolbox is not moving, its displacement is 0, so the mechanical work done is 0. A second situation, so if a puck on an air table is moving, it would experience negligible friction, and it would tend to not sort of stop, so no force would be applied to it, but it would still be moving in the velocity that it was, the velocity vector it originally left with. So it could still have a displacement in the horizontal direction where no force was applied. So another situation, let's say you an asteroid is floating through space, so one that's not going in a circular kind of motion around a planet, so just a rogue asteroid. The force that got the asteroid moving, let's say it's long gone at this point, and the asteroid's just moving with constant velocity. No work would be done because no force is being applied to it, even though it is moving. Another situation here, here we have a pair of figure skaters. One figure skater is holding the other above his head, and he is moving horizontally and she is moving horizontally, but his force is applied vertically, and in that case no work is being done in lifting the girl because there is no displacement in the vertical direction. So those are situations where 0 work occurs. Either the force is 0, the displacement is 0, or the force is perpendicular to the displacement. So here's some questions to think about. A student pushes against a maple tree with a force of 250 newtons. How much work does the student do on the tree? Well, it doesn't say the tree is moving here, so the displacement is 0, so 0 work is done. This is the question I kind of gave earlier. We have a 5,000 kilogram meteor just traveling through space far from any measurable force of gravity. If it travels 100 meters per second for 1,000 years, how much work is done on the meteor? Or the meteoroid? And since no force is acting on it, the work done is 0 in that case. Another question, we have a nurse holding a newborn baby who weighs 3.0 or has a mass of 3.0 kilograms. She holds the baby at a height of 1.2 meters off the floor, and she carries the baby for 15 meters at a constant velocity along the hospital corridor. How much work has the force of gravity done on the baby? 0. The force of gravity hasn't moved the baby at all, so the force is perpendicular to the displacement, and again, 0 work is done. You could also calculate work from a graph known as a force displacement graph, or a force position graph, which is a graph that you see here, also called an FD graph. Because force is equal to work is equal to force times displacement, the area under this curve of this graph would be equal to the work done. So let's look at another situation. What if we have work, how do we represent negative work in this situation on this graph? Well, if the work, if the curve or the function is below the 0 on the y-axis or the f-axis, then we'd have negative force, and we'd have a negative force, or we'd have negative work done. So the first two situations where we had rectangles are situations where we would have a constant force applied, but sometimes force is not applied at a consistent rate over time. So in this case, we would have the force being varied with the displacement or the position. So if that situation happens, finding the area underneath is a little bit more complicated. Here would be a triangle, and we're really just going to deal with triangles and rectangles for this course, but the concept is you need to find the area underneath the curve, the f function, to find the work that's done. Here's some notes to copy down for graphing work. It's positive when you're above the x-axis. The work is negative if you're below the x-axis. Work may be determined from the force displacement or force position graph by calculating the area between the graph and the x-axis. And let's look at a problem here. It says the graph shows the force acting on a cart from a spring, and the force from the spring is either in the same direction as the cart's displacement or in the opposite direction. So we have an A, B, and C region on this graph. So we're asked to calculate the work done. Well, for A, it's simply 5 times 2, which is 10. For B, it's 1/2 of 5 times 1, so that's 2.5. And for C, it's negative 1/2. Sorry, it's 1/2 times negative 5 times 1, which is negative 2.5. Interestingly enough, the work done in B is counteracted by the work done in C. So if we're asked to determine the total work, it is the work of A plus the work of B plus the work of C. And that is really just equal to the work of A, because B plus C would be 0. So we have 10 joules of work done in total. Why is the work in section C negative? Because the force is being applied is negative in this case.